here, this is in part 4. Thank you. This is LeChatlier's principle, which is actually what you're going to be doing tomorrow. Tomorrow you'll be stressing the systems, and based upon what we've talked about in lecture, you should be able to actually anticipate what you're going to observe. But you're going to write down your observations. Carl and I, Dr. Snipes and I, we're talking about this, and it's like you guys don't have any calculations that will be due for your lab write-ups, but you have like 10 billion equilibria, chemical equilibria that you need to include in your lab write-ups and kind of discuss the equilibria. There's like 5. There's like 5 little reactions that you're going to be doing tomorrow. And you're going to be stressing each one different ways and anticipating what's going to happen.
That's a big difference.
What's that?
That's a big difference. 5 and billion.
Okay. Oh. All right, 5. I think there's 5.
Then you're not teaching me math.
That's right.
So.
Somebody else does that. Where they get it. So we talked about stressing the system by adding or removing a reactant or product, and we met on Monday. And now we're going to talk about other ways to stress a system that's in equilibrium. So this one actually is going to be involving adding or subtracting heat. And it depends on whether it's an endothermic or an exothermic reaction. And we've talked about that in Chem 1, now we're in Chem 2. If it's got a positive enthalpy, heat of enthalpy, then you know it's endothermic, and we can kind of think of heat as a reactant. So, now in this case, basically you end up with a different Kc. Your equilibrium constant is different at different temperatures. So adding heat is actually like adding a reactant, and we said it's like tug of war, only opposite, so you're pushing. So you would expect that the product side to be favored in this new Kc. So you're, like I said, you're going to have a new Kc, and your Kc at your higher temperature is going to be larger. Why? Because it's endothermic, and we can think of heat as a reactant.
I don't have the previous slide blank filled in.
What? Did it die?
I didn't get it either.
Oh,
Unless you had it on there. And I
this
just,
one.
Yeah. Okay. Thank you.
I got ahead of myself. Yeah. I thought that was like, oh my gosh, I just jump right into endothermic. So we're going to talk about endothermic and then exothermic. Yeah. This is, thank you. So this is a little bit different than we talked about adding a reactant or adding a product. In that case, you end up with a different QC. You compare the QC to the KC and know which direction you're going. In this case, you get a new KC. You get a new set of equilibrium concentrations of reactants and products.
All right, so you have a reaction that's in equilibrium and you add heat. You're changing you can change the
Assuming,
KC
yeah,
of
assuming
that?
you add heat, in fact, assuming you add heat and it's adding new temperature. So you basically, your temperature, you're running at 20, your equilibrium 20, now we're going to run it at 30. So
Okay.
yeah, you add heat and your KC is going to be higher.
Okay.
Yep, if it's endothermic.
If it's in.
Yeah, if it's endothermic. Exactly. So you get a new KC. Okay, so this is a little bit different. Your KC will be higher at the higher temperature, will be greater. Your KC will be greater at the higher temperature than at the lower temperature if it's endothermic. That's why whenever you look up equilibrium constants, it has to give you a temperature. Yeah, it would always give you a temperature. So let's change it up a little bit, and let's say, what if your equilibrium is exothermic? Well, if it's exothermic, we consider heat a product. Of course, your enthalpy, your enthalpy of the reaction will be negative. And so in this case, if we add heat, it's like adding a product, which is like going to push it back. So we're going to actually, for a little bit, we're going to favor the formation of our reactants, which is in the denominator of our Kc expression, our equilibrium expression, which is going to end up making their Kc smaller. So if it's exothermic, then at the higher temperatures, your Kc will be smaller. Okay? And however you want to think about that, but that's why it's happening. Then at the lower temperature. Okay, Okay, so we stressed it by changing concentration of reactants or products. We stressed it by changing the temperatures, and we're going to be doing that tomorrow, both of those tomorrow. Okay, here's another one, and we won't be doing this one tomorrow. And this one only happens, best happens, I guess, is most noticeable if your reactants and products are all in their gaseous phase. So assume that you have two reactants that are gases, two products that are gases. There's your equilibrium constant expression. And we're going to change the volume. Now, in order to I'm going to show you the bottom line here, and it's pretty straightforward. I have like a one statement to summarize the effect of changing the volume if your reactants and products in equilibrium are in their gaseous phase. I have one sentence. I'm going to kind of talk you through it. Our equilibrium constant expressions are always in terms of molarity. So molarity is moles per volume. That's what molarity means. All right? So we can kind of think through that. In this case, we can basically, for each of our products, C and D, we can get molarity, moles per volume, all raised to stoichiometric coefficient, which is the equilibrium constant expressions way. And here's the products. Now, these V's are all common because they're all banging around in the same container. So the V's are the same. Of course, the N's are the number of moles of the products and the reactants. And the little c's, the exponents, are their stoichiometric coefficients. So we can't cross out the v's. We cannot make the v's all go away. But what we can do is combine the v's. And that's actually what's done right here. We're combining the term 1 over v. If we do that, if we pull that out of the molarity term basically, we need to recognize that we're taking 1 over v times the quantity raised to the power c plus d minus, because they're in the denominator, a plus b. Okay, so that's all over here. This is a proof again. There's like one quick statement to show you the effect of changing volume on an equilibrium like this. Well, let's go ahead and clean it up just a little bit more. I don't like the 1 over v term. We can clean that up and just make it v if we basically take -1 times the exponent. And that's actually what's done here. So now we're getting closer to something that I kind of want to show you. Okay, so little a, little b are the coefficients of your two reactants. Little c, little d are the stoichiometric coefficients of your two products. All right. So let's kind of think through this. But before we think through this, I actually did kind of a fast one. We talked about reaction quotients on Monday. That's a snapshot. Reaction quotients take on the same form as your equilibrium constant expression, but it's a QC. It's not necessarily at equilibrium. So I substitute a reaction quotient there. Now, let's sort of kind of think through this. So if that power of volume, the power of volume is quantity A plus B minus quantity C plus D, if that power is positive, then if you increase the volume, then you're actually going to increase your reaction quotient. If you increase your reaction quotient QC, what we said before is that basically now you have too many products. Your products need to go back to form reactants. That's just consistent with what we've been talking about, or I guess we just talked about on Monday, reaction quotients. Products must be converted back to reactants to get to equilibrium. Okay? And again, I'm going to summarize this on the next slide. If instead your exponent of V is negative, in that case, that will be the case if you add up your stoichiometric coefficients of A and B, and if they're less than your sum of your stoichiometric coefficients of C and D, you're going to get a negative exponent. And if that's the case, then when you increase volume, you're actually going to decrease your QC, your reaction quotient is going to be less than your KC. And if that's the case, what we said is you basically have too many reactants, and your reactants need to go to form products. So it kind of comes down to, and the quick and dirty, the rule of thumb that I'm going to show you is basically going to look at these stoichiometric coefficients. Those are just the stoichiometric coefficients of your reactants and products. Bottom line is this. If you have species at an equilibrium that are in their gas phase, they will be affected by changing volume. And it kind of, I kind of did the proof just a minute ago, but it basically, the side, the reactant of the product side, whichever one has more moles, favors increasing the volume. Kind of makes sense. I like it. Okay, and we're going to look at an example here. So you just look at the coefficient. You know how many moles are reacted or how many moles are produced. Look at the coefficient. Whichever has the more moles, that one, when you increase the volume, is going to be favored. Now, the opposite is true. If you squish it down, decrease the volume, then it's going to favor the side with the fewer moles. That's it. So in this example, forming water from 3 moles of reactant to 2 moles of product, if we go ahead and increase the volume, that would increase actually the 3 moles. Increase the formation of the 3 moles. So if we increase the volume just temporarily, and I kind of think about it this way, just temporarily, we're going to see this sort of thing. It's going to go back that way and continue going this way to a lesser extent, temporarily. That is the deal. Lucille. Okay. So if you increase the volume, it increases the side. Now, I will warn you, and actually your homework is going to pull this out of you. If in looking at the equilibrium you see anything with an S, what does S mean? If you see anything with an S, it doesn't count for moles. Okay? If you see anything with an L, it does not count for moles. So it's just the moles of gas. Whichever one has more, side has more, if you increase the volume, that will be produced more. If you decrease the volume, then the one that has fewer sides of moles will be produced more. So watch out for those S's and L's. Okay, so I think I have an example and kind of a proof to kind of finish up here. This is kind of like we did with part 1 a little bit. Again, picking on the Haber process, which is the formation of ammonia, excuse me, darn it. Ammonium's the cation, the neutral molecule ammonia. Okay, so the little e's, I love the little e's. Sometimes they're not always there, but of course you know that means equilibrium concentrations. So we're saying at equilibrium, these are the molar concentrations of the 2 reactants and the 2 products. All right, so we could go ahead and one of our first things is to knock out what is the Kc, the equilibrium constant for this equilibrium. And then we're going to change the volume. And I'm going to tell you that when we change the volume, the Kc remains the same because it's the same temperature. So let's write the equilibrium constant expression, be the molar concentration of the product raised to the 2nd power, divided by the molar concentration of the reactants raised to their stoichiometric coefficients. Let's plug in, and we got, do you guys already have this? Okay, good. Those numbers then are the molar concentration of ammonia in the numerator and nitrogen and hydrogen in the denominator. Remember, this is kind of fun because this is finally something in chemistry that we don't have to let units cancel. We know they're canceling behind the scenes. Rounding to 3 significant figures, our Kc, our equilibrium constant, is 0.0610. All right. So the little proof we're going to do now is to take the same system that's, I like to say, minding its own business at equilibrium, and we're going to double the size of the container. Okay? And I'm going to prove to you that in doubling it, first I'm going to prove to you that in doubling it, we're going to come up with a QC, a reaction quotient, and it's not at equilibrium. Our QC will not equal this. Okay? I know it's weird. It is weird. And put it this way. If you double it, I don't know if this is right. Maybe this won't work. But I think if you double it and you have the same number of moles on each side of the reaction arrow, equilibrium arrow, I don't think that changes any. I think it stays the same.
Makes sense.
But here it's raised to different powers. I'll show you how this works. But in the numerator we have a squared term, in the denominator we have it to the 1st power and to the 3rd power. Yeah, I think so too. So in order to kind of think through this, okay, I'm going to show you how we're going to do it. But before we think through this, what we're trying to prove here is that hopefully you guys should tell me which side will be favored. for increasing the volume. Yes, the reactant side. Let's see if that's true. It should be. Let's prove it. Well, we got to step through this whole thing. Because remember brackets, one of the things I run into with students is when you see brackets in, like for instance, an equilibrium constant expression, you have to use molarity. You can't use moles. Yeah, for heavens can't use grams. It has to be used molarity. So we have to find the new molarity of everything. So for instance, the new molarity of nitrogen, it was 0.921 divided by 2. Now we got 0.461. The new molarity of hydrogen, 0.763 molar divided by 2 is 0.382 moles per liter. Okay, we're doubling the volume. The new molarity of ammonium is that original 0.185 moles per liter divided by 2. It's diluted by a factor of 1/2. Now we have a new molarity of 0.0790 moles per liter. So the first thing I told you we're going to do now, we're basically going to take those molar concentrations and plug them back into our Kc expression and or reaction quotient, our snapshot. And what I'm going to prove to you is that that does not equal our Kc anymore. I feel like a magician sometimes. I'm going to prove to you. So here we go. So notice it's a snapshot. We plug in the numerator, we have the new molar concentration of ammonium, 0.0790 squared, divided by the molar concentration of nitrogen, 0.461 raised to the first power. Also in the denominator, 0.382 raised to the third power. Rounding to 3 significant figures. Drum roll. If you're like me, this whole squared and cubed, I have to do it a couple times to make sure I get the same answer. Okay, around to 3 significant figures, we got something different than our Kc. Now it's 0.243. And remember we said if you want to know which direction your equilibrium needs to go in order to reach equilibrium, you can compare your reaction quotient with your Kc and make a judgment call. In this case, our reaction quotient Q is greater than our equilibrium constant K, or Kc. So if it's too large, then you need some of the products to go back to form reactants. That's exactly what you guys told me should be favored, is the reactant side, because it had more moles of gas. Okay. Ta-da! A little proof to prove it to you. Okay, so let's look at another example. Is this endothermic or exothermic? 50-50 chance, starts letter E. Is energy released or absorbed? It's endothermic, yeah. Why is it endothermic? Because it's a positive enthalpy of reaction, exactly. So this is endothermic. So we can think, where will heat go? Will it go on the reactant or the product side? Reactant side. Yep. We'll think of it. It will go over there, exactly. Yep. Okay, I can't remember. Oh yeah, I was like, what is this problem? It's okay. So this is like on the test and in your homework, sort of things you're gonna run into. So we put heat on the reactant side. Now, what happens if in this tug of war? Oh, by the way, what happens if? And this is classic. Okay. So this is all what will happen to the moles of NO. So throughout these questions, what happens to NO? What happens to NO? That's your question. So what if NO is a product. What if we add more N2O3? What will happen to NO? How many people think it'll go up? Me too. Very good. You buy that? So I'm always going to ask, will it go up? Will NO go up? Will NO go down? Or will NO stay the same? Okay, let's see, we're gonna add more NO2. How many people think NO will go up? How many people think NO2 will go down? Me too, why does it go down?
I'm kind of thinking of it like a math way,
Okay,
kind of, because since you add more, it's going to be a smaller number.
yep, gonna have to be a smaller number, very good. Okay, I'm liking it. Yep, number of moles of NO will decrease. Group test, I'm thinking it. No, group test. Okay, what if we remove some of the N2O3? Remove some of the N2O3, what's going to happen to the NO? Remove N2O3. How many people think it will go up? How many people think it will go down? I just kind of paused because more people look like they're going to say, why do you think it will go down?
Because the N2O3 decreases, the NO should decrease, right? To equal it out.
Yeah. You can think of it so many different ways. I think of it a tug of war. You can think of it as the N2O3 going away, and it's going to have to basically work harder to make more N2O3, so it's going to go down. Or you can think of it mathematically, and your equilibrium constant expression and your Kc expression would look like this. Okay, so if that, what do we say, if this goes down and this has to stay the same, by golly, that better go down too. This goes down, that needs to go down, and that the same. LeChatlier's principle. Yes, NO will go down. All right. Did you guys get that? Probably. The next one, increase the volume of the reaction flask. I'll give you a minute. Increase the volume. Make the volume bigger. Those are all gases. And we're after NO. Make the volume bigger. How many people think it will, did I start with increase usually? How many people will increase? Me too. It will increase. Why will it increase?
There's more moles on the product side.
Mm-hmm. There's more moles over there. There's 2 moles to 1 mole. So increasing the volume increases both reactant. Well, excuse me, both products. NO will increase. And last, but certainly not least, I think it's last.
No, one more.
Oh, darn, there's 2 more. Okay. So we're going to lower the temperature. Now, you guys told me it was endothermic, so we put heat over there. We're going to lower the temperature. We're going to get a new Kc, and our new Kc is going to actually have a different value, obviously. But if we lower the temperature, I'm thinking through this too. See, that's how I do it. I haven't done this one. Lower the temperature, removing some heat. Okay, so we're going to go up, down, or stay the same. So how many people think that NO is going to go up? How many people think it's going to go down? Why is it going to go down?
Because the reactant side's losing temperature, so if you put it on there, it lose stuff, so you NO will have to go down
Yeah,
too.
that's what it,
Isn't it that like there's less product to cause like less heat? So in a way, like
Lowering the temperature.
lower the temperature so the less heat is produced.
Could be.
I just saw it as the heat, you're adding it to the N2O3, so you're like adding it to the reactant side. If you take away heat, that's going to go down, so then the NO would have to
yeah, I
go
kind of
too.
feel like, yeah, because didn't you say, because the heat goes over into the product side, and so when you take away the heat, and then there's, yeah, not as much.
Yeah, it kind of pulls it back. That's how I think of it, kind of. I do. All right, last one. So the number of moles of NO will decrease. You're right, because it's endothermic. Now, last but not least. Okay, so we are going to add an inert gas. It's classic. We're going to add helium. Now, you don't see helium anywhere in there. We're just going to basically pressurize the thing with helium. I'm curious. How many people think that NO will increase? Decrease? Stay the same? Stay the same is the right answer. Yeah. And this is one of those things, you might want to go back and read Petrucci in this chapter and what he has to say about an inert gas. It's just there. It's not a partial pressure of anything. It doesn't appear in your KP expression, wouldn't appear in your KC expression. So it's just along for the ride. It's kind of a medium sort of thing. It's like if this were happening in air or a vacuum, that's a good example. But those particles are going to do what they're going to do and establish their equilibrium according to the temperature and the KC at that temperature.
So is that saying it adds it to the reactant side or adds it to both sides?
Adds it to both sides. I mean, because you
So that
figure
makes- yeah, that makes-
this whole thing is one happy mess
Mhm.
in the same container.
I was thinking it was adding to the reactant side.
No, it says you're just basically going to take the flask that's at equilibrium. It's at equilibrium, mind its own business, and you're going to pressurize it.
So if you're increasing the volume of the reaction flask, it's simply like more space for more reaction to occur?
Mm-hmm.
Okay. So
Yep,
that's why there's
yep,
more.
and it favors the side of the more moles.
Okay.
Yep, yeah. That makes sense. It's like stretches out. It's like whoever's got more moles. Okay, so, yep, number of moles, it does not have an effect on the molar concentrations of anything, including NO. So no effect. So let's take a look at the homework that's due on Friday. I can't believe we're here to Friday already. And these, I was looking at these and I was like, oh my gosh, and then you don't have to get your calculator out for these. It's just kind of weird. My kind of problem, right? And in this class, you don't even have to write in complete sentences. 1.57, this one right here. All right, so 57 looks like this, just kind of like we just talked about. Again, watch your S's for that one problem. Okay, one question. So for the first one, for instance, it says, what if you raise the temperature? Have a new hotter temperature, equilibrium temperature. Note that it's exothermic and it's like adding a product because heat is on the product side. That's just my hint. Oh, by the way, all of these are saying what will happen to, we focus on NO. This is all what will be the concentration for H2. This is focusing on H2. Okay, so it's just like what we did. And I probably shouldn't belabor these too much. What if you introduce more reactants? Okay. Now C, don't forget I say that this only works with moles of gas. So actually within this equilibrium you need to focus on if you double the volume, if you increase the volume, it's going to favor the side with more moles. Wait, which side has more moles? That's exactly what I was trying to tell you a little bit ago.
Reactant side?
More moles of gas.
Oh, gas. Okay, so they're the same.
Yeah. So
Yeah,
I don't
good
think it will change. Yeah. Okay, and then the last one, what if you add a catalyst? And this actually goes back to one of the things we covered in the previous unit. Catalysts only allow for an alternate mechanism, so the speed at which equilibrium is established will change, but not the equilibrium itself. No effect. So 58, kind of similar. I don't think there's really too many catches. Here's 63 and 64. My hint for 63 is don't forget to only focus on things are in their gaseous state for changing the volume. And then this one down here, 64, identify if it's endothermic or exothermic, and so we expect the forward direction, what will happen to the forward direction if you increase the temperature. So you should be fine with that. Okay, now on to something that you will use your calculators for. Okay, looks like this. And my hope is to get to the first assignment slide, so we shall see. So this is going to make you reminisce a little bit about things we covered in Chem 1. But we've been talking about key in equilibrium constant expressions, okay? And actually, if you have a chemical equilibrium and somebody gives you the balanced equilibrium, And we can write a KC expression for that, no problem now. But I'm going to try to convince you that you can come up with what the concentrations of everything, reactants and products, will be at equilibrium if you are given the initial concentrations. And I think the first problem I'm going to bring out what they call an ICE chart, an ICE chart. I like them, your textbook uses them. If you give the initial, we're basically going to take something that's not at equilibrium. And we know the initial concentrations. And if you know one of two things, if in addition to the initial concentrations, if you know, either one concentration of one species at equilibrium, that's going to be your E in your ICE charts, or if somebody gives you the KC or the KP or whatever it is, your equilibrium constants. And that's in terms of molar concentrations or partial pressures. So you have to know the initial concentrations, and either, your options are also an equilibrium concentration or KC. So today what I want to do is this one, where you know the initial concentrations. Basically, these are concentrations of species, reactants, and products as they are not in equilibrium, and you are given one equilibrium concentration. So what I'm going to try to show you is that you can backtrack. In fact, I'm going to go ahead and start to show you an ICE chart. I don't know, I don't think Dr. Snipes does it this way, but I do. Okay, ICE. I stands for initial, C stands for change, and E stands for equilibrium. And basically you're going to have columns of reactants and products here going across from left to right. So that's kind of how this works. So we're just going to jump in there and do a problem. So let's see if we can go ahead and start filling out an ICE chart. Now, I've done it differently, different year, different semesters, but I'm just going to start from left to right. I'm going to put my reactants and my product up here. So I'm going to put the molar concentration of N2, the molar concentration of H2, the molar concentration of NH3, and somewhere in the margins I'm going to knock out my equilibrium constant expression. Kc is equal to, it's always products over reactants, so it's NH3 raised to the third power divided by the molar constant, second power, my bad, you guys would have caught that. NH3 raised to the second power divided by the molar concentration of N2 raised to the first power times the molar concentration of H2 cubed. Okay? All right. So suppose we start with initial concentrations. So that's my I, isn't that? Suppose we start with initial concentrations of 1.00 molar for the two reactants. So I got this. Okay. Initial concentration for ammonia is 0. Now, notice that that's in parentheses. If they went ahead and started the problem, suppose we start with initial concentration of 1.00 for each of the two reactants at some temperature of interest, and then went ahead and did the problem, you would have to know that since they didn't say anything about the initial concentration of the product, there was none. Okay, so you're going to have, it's a subtle thing. When equilibrium is reached, the concentration of N2 was found to be, dun dun dun, make sure I got my right thing here. N2 at equilibrium is 0.921 molar. Probably somewhere in here I should go ahead and jot down the stoichiometry, which I'm going to have to know. 1 mole of N2 reacts with 3 moles of H2 in equilibrium with 2 moles of NH3. All right, so far so good. So we are supposed to calculate the equilibrium concentrations of the other reactants and of the product. So we're supposed to fill in those blanks. And we're supposed to come up with a value for this. Well, of course, if we come up with equilibrium concentrations for these three things, bada boom, we got KC, no problemo. But it's really not that hard. Do you see where, let's see, do you guys need anything here? Okay, guess not. So this C in the ICE table stands for change. The change, of course, would be, what's the difference between what it started out with initially and what it was at equilibrium. So the change is 0.079 moles per liter. And do you buy this, that for every 1 mole of this that reacts, 3 moles of this reacts? Does that make sense? 3 moles of H2 reacts for every 1 mole of N2 that reacts. We're going to use that to come up with this change. This change right here, and this is where I'm not probably going to fight you on labeling things, but if we simply take 3 moles of H2 for 1 mole of N2, and basically take the change of N2 is 0.079 moles per liter of N2, okay, that will give you a change of 0.273 moles per liter for my H2. We're going to do a similar thing over here for this change right here. And the relationship is a 2 moles of ammonia for every 1 mole of N2. Again, times 0.79 moles per liter N2. Okay. And that is equal to 0.158 moles per liter. This is kind of like a thing that well, not kind of. This is one of the things we talked about in Gen Chem 1. So if you buy that, then in an ICE table, the next step is to basically apply the change. So what we do in an ICE table is take your initial, apply the change, and come up with an equilibrium concentration. So on this slide, for instance, for H2, we started out with 1.00 moles per liter. Our change was 0.237 moles per liter. Our equilibrium concentration is 0.763 moles per liter. For ammonia, we had 0 to begin with. Our change was 0.185 molar. 0 plus 0.185 molar is 0.158 molar. One of the things I did not emphasize, I'm going to grab a red here, is that because of, and we'll be talking more about this on Friday, because we had some of each of the reactants and no product, okay, our change for both of our reactants was negative. Okay, initial plus change, and these are negative. Here, our change was actually positive, so there actually is a sign to that. All right, so then the last thing we got to do, all we got to do is take these numbers along the bottom, if you use an ICE table, which I like, and plug them back into our KC expression. So we can knock out a value for the equilibrium constant by, in the numerator, taking 0.158 squaring it, and the denominator, we're going to take the product of 0.921 to the first power times 0.763 raised to the third power. Rounding to three significant figures, we can have a value, a KC value of 0.0610. So in other words, we basically took these and plugged them back into here. Whoops, I didn't do that one right. This one goes here. This one goes here. This one goes here. And then this one goes up here. That's better. All right. So let's take a look at the problems that are due for also on Friday. They look something like this. They look very much like this. $15, $17. All right, so if you read it a few times, you know, all the problems are different. That's one of the things that we fight against in chemistry. You can see the chemical equilibrium kind of been embedded there. So equilibrium constant expression, of course, looks like that. It's always products over reactants. If you read it a few times, you'll notice that they don't give you molarity, but do not use moles. Do not, unless you want to get it wrong, which I don't think you guys want to get wrong. Do not use moles in a Kc expression. It has to be molarity. So we're going to have to divide those moles by their volume. Notice in this case, it's kind of like this case where we have the reactant but no product. Okay, and they do give you at equilibrium the molar concentration of one of the two products, which stoichiometry would say, what do you think? Probably and this is balanced, right? Yep. So it's probably this. Does this make sense to you? Don't you think this molar concentration is going to be the same as this one? I do. So you got the change, and you can use stoichiometry, which is a 1 to 1 to 1, to get that one. And then you're just a hop, jump, and a skip away to getting that equilibrium concentration. So, okay. Stoichiometry kind of helps for this one. Notice that your change for that one, I guess it's a little different. Yeah, no, the change will be negative for your reactant and positive for your products.
So when we're working this out, we should have the proper signs.
Yeah, I think it would be good. I think it will be helpful when we get to actually acids and bases, pH chemistry. I thought you were going to say, so when you're working that out, do you have to use an ice table? No. But do you have to show all of your work? Yes. So one way or the other. You can't just put something in your calculator and assume that I know where it came from, because I'll just put a big question mark, even if you get the right answer. So then it's kind of similar to knock out the Kc expression, or excuse me, the value for Kc is to substitute in the equilibrium concentrations. And I think they're all a little bit like this, with just maybe a few catches. I don't know. This one's very similar. In this case, they don't give it in moles, drat. They give it in grams. So you have to look up use the periodic table, knock out molar masses, get moles, divide by volume to get molarity. Okay, you can do it. I do, like I said, like the ice table, because later on it's probably more obvious to use it than it is for here. But in this case, just kind of looking at my notes, I can see that in this case, you have some reactant and you have some product, but you don't have any of the second reactant. Okay, so it's a little bit different. But in all of these, you are given the equilibrium concentration of something. So it's kind of like playing backwards, kind of, I think. From this equilibrium concentration, you can get that change. And if you can get that change, you can use stoichiometry to kind of plug over and get the change of the other two things. That's the way I think of it. And it's not as straightforward whether, kind of like you said, Marie, these green things right here, it's not as straightforward if change is going to be positive or if it's going to be negative later on. And these, it's pretty obvious. It should be pretty obvious. So you take your initial, apply your change, and then you get the equilibrium concentrations, and then you just plug them back into your equilibrium constant expression. And last but not least, see, there are fun. This one I went ahead and balanced for you just in case, so we're all kind of on the same page. You know, the equilibrium constant expression looks like that. Ice table looks like this. Notice we just have some of the reactants, none of the product at first. Looks like they give us the equilibrium concentration of the I2, which is one of the products. So you can get the change then, and then you can spread that change out to the other product and the reactant. Once you have changes, you can apply those changes, come up with the equilibrium concentrations, then plug them back into your equilibrium constant expression to get a KC. Phew. So you didn't use your calculator for the other one, but you really need to use your calculator this time. Makes up for it. All right then.